My name is Bernhard, and my surname is pronounced Emese. This is an Hungarian name, and I'm known by somebody, a few, by Panamatic, which is my company name. I want to talk about the HP-19C today. This is the first and only handheld scientific printing calculator, as I know. There is no other handheld. The followers are the HP-19C, which are desktop calculators already. So my next question is, does anybody know the HP-19C or even own the HP-19C? Okay. The other question, who does not own the HP-19C and want to own one? 1, 2, 3. For this purpose, I have a picture. I have only 10, so I hope. Who wants to own HP-19C? Please. And here are 3 more. The purpose of this presentation is to show you some overall concept of the HP-19C and some curiosities, or shall I say secrets, about the internals. I acquired my first HP-19C 5 years ago, I think, or 6 years ago, and it was, of course, bought by eBay, and I had the very low price of 45 euros for the item. Normally they are much more expensive, but it was also signed as defective, so I didn't expect anything. But what I got was a totally corroded HP-19C. It was like being underwater in salt water for several years in a sunken submarine. And I can show you the display of it. You can go around. I don't know if you can see it here. It's too small. This is just copper chloride and nothing left. Just green salt inside of the display. And the other boards were like the same. Well, I was not, it was okay. And in the next time I was thinking about repairing it. And this is one of the topic of today, in the second part of this presentation, how far I am to have repaired this calculator. But first, the overall concept. This calculator is a handheld. As you can see, you can hold it in one hand, and it has a printer inside. You can switch on, and you can press the print button, and the thermal printer will print what is on the display. I think it was invented in 1977 or even 76. It belongs to the Woodstock calculator family, to the HP-2520, and it is the twin calculator of the HP-29C. They have the same architecture, but the printer, of course, is added. The HP-29 has also 98 program steps, 30 storage registers, and the software was compatible between these both calculators. What you can see here is a part of the memory of the manual, and this manual is a combined manual for the HP-29C and HP-19C. So, what is the concept? This is the main board. And what you can see is the so-called ACT processor, arithmetic control timing. This is the main processor which makes the instruction decoding and the calculations. This is also in all other Woodstock calculators contained. And I was able in 2015 to make a replacement for this chip, just to repair my own HP-25 calculator at that time. And because I was successful in this repair, I thought I could also do a repair of the HP-19C calculator by taking the same replacement chip here. But this is not enough, because this bigger chip here is a special development for, I think it was developed for the HP-90 series, the 97, and it was used also then for the HP-19C. This chip has the capability of reading more key buttons for up to 50 keys, which is not possible with this chip alone. This chip, ACT, was able to read up to 35 buttons. And you know that these calculators, the Woodstock calculators, have about 31 or 30 buttons, and the HP-35 had exactly 35 buttons, the previous. What you can see is this PIC chip, printer interface keyboard. So this chip has the capability of reading a bigger keyboard and to control the printer output. It has also the possibility to control the motor of the printer. So it can control the motor speed and can start and stop the motor, can brake the motor for the more sudden stop. And this is all what this chip does. But it communicates with this ACT. And this was my repair problem. I chose a processor for my replacement which was not able to communicate to the real PIC chip. But later more of that. What you can see here is a RAM, 16 registers. A register is 56-bit and can store one number. And so one RAM can store either one number or 7 program steps. This is another chip RAM with 16 registers, and this is a third RAM which can also store 16 registers, but the difference is these two are CMOS.
Sorry, so it's one interruption.
It's a...
So, okay. I'm going on. These RAM chips are CMOS RAM for having the continuous memory. So when you switch off the calculator, you still have the memory contents when you would switch on again. But not this RAM. This is just lost if you switch off. Then these are ROM chips, read-only memories for the operating system, for the code, which are the instructions. And this is the display driver for the anode segments, and this is the display driver for the 13 digits, the cathode. That's all. There is a little bit reset circuitry, and there is a transistor which can switch on and switch off the display for some purpose. And this is the main board. Here is the connector to the keyboard, and here are connectors to the printer board, which is below the main board. And this is the connector for the display. If you like have information, you can download this document later from my website. And I want. Oh, sorry. This can be downloaded from my website if you want to have more information about HP-19C. I will not repeat anything here. But this is the second board, the printer and power supply board. This is the power supply which produces 6.4 volts and
The
minus.
microphone isn't your enemy.
I never use microphones.
Okay.
I have 3 microphones, yes.
Yeah.
And nothing works. Okay. And the rest of this board is used for the transistor drivers for the printer pixels, which are connected by this flex cable, and here's the printer with its mechanic and its print head here. The schematics of the HP-19C are drawn by Tony Dill. I don't know if I pronounced that right. And it is very good. All calculators of this era have schematics in this form. I myself made the schematics in this way because I wanted to understand everything and wanted to reproduce the keyboard, if the printing board, if necessary. This I don't want to go into detail here. The LED display of this calculator has 13 digits, and this is 1 digit more than the HP-25. Why? The only reason for it is because the decimal point has a separate digit. This is the only reason for additional digit. And interestingly is that this pinout of the LED display is compatible to the pinout of the HP-25 display. So you can replace my totally corroded display just by inserting an HP-25 display. You only lose 1 digit. And when I replace the ACT chip, if I will be successful in the future, then this is not necessary because I can adjust and show the decimal point in a separate, not in a separate digit, but together with a number before the decimal point. So it will be a complete replacement of the display possible. Next is the print head. This small white piece is the print head. It is a ceramic with aluminium traces, and here are 7 single pixels. And while the motor drives from left to right or right to left, these pixels are heating up, and the thermal paper will getting blue. And this is the method for printing. So if the motor goes fast, you have very white characters. If the motor is slow, you can have very more narrow characters. In today's thermal printers, of course, you have no moving parts except for advancing the paper, because there is a print line over the whole line. There are many pixels. Now we come to the part which is more interesting. They are the curiosities of the HP-19C. I will start with this, which you perhaps know. The HP-19C has a display where the logo of Hewlett-Packard is seen in the decimal point of each digit. So what you see here is the decimal point, and it's the HP logo seen inside. Just for fun, they made it, I think. But now I can tell you something which nobody knows. When I made the replacement of the HP-25 ACT, I had to send signals to the display driver for producing numbers, and there are 4 bits to send for each digit to the display driver. In these 4 bits, as every knows, you can code up to 16 characters. And for the 10 numbers, you use 10 from 1 to 9 and 0, and you have left another 6. 1 code is necessary for the blank. So we have 5 characters. And the HP-25 indeed uses some characters. It could display the name error. An error means there's an E, a small character R, and a small character O. So these are used of 3 characters. And then there is let's go back to the HP-21, which was the predecessor of the 25. It could display error, but nothing else. So there were 2 characters left, which were never used, and they were coded in the anode display driver. So I was the first, with my replacement chip, to send these never used codes to the display driver of the HP-21. And what appeared, do you know what appeared on the display?
An H and a P.
An H and a P. So this is a hidden Easter egg in the display driver of the HP-21. Never used 2 characters was H and P. And this is related also to this logo which is in the HP-19C. And then this is even more interesting. The engineers thought this is enough of this joke. We need these 2 characters for our purpose. And the HP-25 was able to show an arithmetic overflow by showing the letters O and F. And the F was not there by the existing display driver. So they redesigned the display driver and replaced the letter either H or P. They replaced the letter P. Yes. So Mr. Hewlett decided to remove Mr. Packard in this display driver. I don't know if they have thrown dice or something, or he has lost a bet. But when I showed all digits of the HP-25 display driver, the letter H, the letter P was replaced by this F, which was used for overflow. But that's not the whole story. The whole story is that the next generation, the HP-67, was using another text on the display. You know, it's the card, C-R-D. Please insert card. So they used the C letter. And then also Mr. Hewlett was removed from the display driver. So what I wrote here is, this problem was settled anyway with the introduction of the HP-67 because it needed to show the letter C to insert a magnetic card, and they sacrificed also the letter P. Let's go on. The HP-19C is the most terrible calculator to work with. By repairing, by opening, by closing, by taking measurements. Everything is fiddled together, 2 boards on top, and if you want to have access on some parts, you have to remove the printer completely, and if you want to reassemble or to close the board, you have real difficulties to switch these golden prongs into the holes, and it is really a mess. I need half an hour to close these calculators, please. So it is a miracle how they mass-produced this calculator. The reason is they developed the HP-19C. It's also, all these things are assumptions. I am not related to HP. I have no internal knowledge, but you can see. They wanted to use existing chips, the ACT, the PIC, and every additional functions, they fiddle together with transistors and some tricky circuits, and that is what you learn when you open and close also the case. My best, the best thing to add these both components is to look through this hole here. There you can see the parts below which must fit into these holes. And there are additional holes which must also fit at the same moment. So if you look here, and then you have to move this distance from here to here and insert and hope that this also will fit on this side. So the next curiosity of the HP-19C is there was really used a multi-layer board for the printer and power supply board. It has 3 layers. The reason is clear. There was not enough space to have the printer and the batteries inside. And every component is very near the next component. Every space is filled up. I have removed all components from this board for a cleaning purpose, and you can see these are the silver traces are top layer, the brown traces are the mid layer, and black is what you can see on the bottom side. And it was not easy to re-engineer the schematics, because even if you remove all components, it's still not easy to follow all these traces. But finally, I reassembled the board with components and new components, and it worked again. But this multi-layer approach was not enough to fit all components on the board. There was another component. This brown component is a kind of integrated circuit which contains diodes, resistors, which are used for comparators, and they are passive components. And this component is soldered on the bottom side of the printer board here, and it is normally flat. This is soldered for, this is bent up for seeing more, and this way they save even more space. Another curiosity is that some wires are put in sockets, 1-pin sockets. These 2 wires are just not soldered. They are pressed into these sockets, and there are all over 5 wires which are connected in this way.
How would that affect reliability, do you think?
Exactly, that is the reason why I tell you this is a calculator which is fiddled together.
Yeah.
The reliability was, I think, not very high with this method, but not as bad as the SPICE calculator.
I know.
So, now this is more interesting. When I acquired my HP-19C in 2015, nobody yet has extracted the original ROM code. You know perhaps that Eric Smith did very good pioneer work on these calculators, and he read ROM codes of the HP-25 and other calculators, but never did it with the HP-19C. And I tried it as the first person, and I discovered that none of the ROMs of this calculator were still working, so they were totally damaged. And for this purpose, I asked Emese, a friend of mine, another calculator collector nearby, and he sent me his HP-19C. It was Harold Pott, you know, perhaps.
You told him that he would open it?
Yes, of course, he agreed. I never do something without allowance. And he allowed me to try to read the ROM code. Then I discovered 4 ROM chips. One is the inside the display driver. There's also 1 kilobyte or kiloword of ROM, and there are 3 others. And this is together 4 kilobyte or kilowords of ROM. But Eric Smith told me he expected that the HP-19C has 5K words to discover. And I was successful in reading these ROMs, but could only extract 4K of words. Then I had no more clues. I set the calculator back to our. And 1 year later, this is the time it needs then I discovered in the schematics, let's go back to the schematics. Difficult to see for you. One more. Moment. Oh. I want to have a bigger view. Can I turn it? Yes. Too much. Got it. So, what I discovered is that 2 of these ROM chips, these are the ROM chips, no, one of these ROM chips had an extra line which is directly connected to the processor, to the arithmetic processor, this number pin 25. And the clue was, this is an extra address bit for the ROM. If this line is low, then you can access the lower part of a 2K ROM, and if this line is high, you have access to the higher 1 kilohertz. So this is a special ROM which contains 2 pages. And then we have the 5 pages. So I was able to read the 5K words. And the result was an application on the PC, an emulator for the HP-19C for the first time, after some more work. So let's go back to this. Next interesting thing is, why do we have 4 to 8 key matrix in the HP-19C instead of the usual 5 times 7 rows and columns of keyboards? The 5 times 7 keyboard system is used by the ACT alone, and this is capable of reading up to, you can do a multiplication, 35 keys. And the HP-19C has only 31 keys, so why not reading the keys with the usual interface? The reason is that for the printer you need anyway to use the printer chip, the PIC chip. And this is also can read more keys, and they decided to use this printer, this keyboard interface contained in the PIC chip, printer interface keyboard. Another reason is the PIC keyboard interface is capable of storing key presses. If you press very fast, 10 times per second, while the calculator is printing, or while the calculator is calculating sinus, sine and cosine, it is still capable of react to the key press. So you can really fast do key presses. This is not really possible with this calculator because you cannot do it very fast. But you can do it very fast on the HP-97. It is a keyboard for you can press 10 times per second. So, and this PIC chip has the 4.8 key matrix. That is the reason why we have this here. So, let's go on. Yes, the strange way how to detect whether a key is held down. It is not possible with the PIC chip to check whether a key is still held down. Just a key press is stored in a buffer. Up to 16 keys can be stored there, but the information about whether the key is still held down is not possible to read with the PIC chip. But sometimes, if you know these calculators, you have the single step button. When you hold down, you see the code, and when you release the button, then the code is executed. And indeed, the HP-19C is capable of showing the code while the key is pressed down. And I discovered in this picture, I can make it a little bit bigger. This is the ACT chip. And as I mentioned, it has a keyboard interface. These are these 5 lines, column 1 to column 5. And not all columns are used, but some of them are connected to somewhere. And one is I should explain how it works. If one of these lines is held down, this will indicate a key press to this chip, to this keyboard interface. And it can, the program can check whether a key is held down or pressed. And what they did, they connected the row 1 of the keyboard matrix just to one of these inputs. And by reading of this simulates a key press. But the key code cannot be read by here. The key code will be read via the PIC chip, but the hold down information of only one keyboard line can be read by this connection. And the result is that you are only capable of check the single step key and the run stop key. And some other keys can also detect it, whether they are held down. But the other keys can never be checked whether they are held down. It just took this single line and gave it the possibility to read it. Okay, now we have the next topic. Oh, this one. Let's go back. Moving the printer motor only in one direction. The printer motor of the HP-19C is capable of moving forward and backward. What you need, therefore, is a more complicated control circuit, the so-called H-bridge, in Germany, H-Brücke. And the HP-19C has a less complicated interface, and the motor can only go forward. The motor shaft is spinning always in the same direction. But a tricky mechanic of this, I don't know, call it roll, or this part is capable that it moves forward and backward, just endlessly. And when a print line is printed, the motor is started, and the blue characters are printed, and then the calculator waits until the switch at the home position of the motor is again reached, and then the motor stops. But it's not enough. The HP-19C prints much faster, because if you have a line which is only short, the number 0.00, for example, then the motor prints only 3 characters and then goes fast backwards. So it has not to move to the end of the line and go back from there. And this optimization is not possible here. But there is another optimization done, because in the hardware, in the schematic, I could detect that the software will apply a reverse motor signal. Reverse motor signal will be applied, and this does not reverse the motor, but it makes the motor drive at fastest possible speed. So after having printed 0.00 in normal slow speed, it goes fast speed forward until the end of the line and fast backward and then break. So it's a little optimization. I think nobody knows about that. it is an interesting small detail. So, I'm already here. Well, this is a picture of this is the display you have seen. I hope I will finish my repair work in next year. Now, what's the time? I want to show you some of the software of the HP-19C. For this purpose, I start the ACT analyzer application, which I wrote for these calculators. Is this big enough to see what's happening? Can you read the numbers? No. Okay, then I have this possibility. Now I choose the HP-19C calculator and run. And this is the continuous memory is lost, it shows error. And now we can calculate and we can enter any number, like number pi with 9 digits and print. And this emulator does really emulate also the printing of this HP-19C. And what I also can show is the code which is executed. Now we have more comments. What I want to show you, just a little example, because this is much too much for explaining the complete code. I want to show you the idle loop of the HP-19C. And now it is waiting for a key press. And if I stop the emulation, then no, this is because I'm just moving too much. Okay. I hope you can see that the processor is stopped at this instruction, and I try to explain a little bit what happens now. This instruction where I'm here says that the status bit 1 is set to 0. I don't explain what status bit 1 is, and I go one step further. Now you know that this instruction will set the status bit 3 to 0. And this I also will not explain, but the next instruction asks if the status bit 3 is 0. So if this instruction sets the status bit to 0, then you would expect that the next instructions always will be 0. But that is not true, because the status bit 3 is a latched input of the ACT circuit. It's the pin number 4. And this pin tells the calculator whether it is in run mode or in program mode. It's the switch between run and program mode. This is directly connected to this status bit 3. So if this status bit 3 is read as 1, then it is in run mode. And if it is read as 0, it is in program mode. And if it is set to 1, it will remain there once. This is latched. And therefore, just before, you have to set it by software to 0. If it is too special, forget it. I just want to show what happens in this idle loop. So this is the check whether the program run switch has changed. And of course, this is necessary in the idle loop. You have to check whether this switch has been changed. The next step in our... Oh, I have to go back.
So by definition, we are looking at microcode.
This is the microcode of the HP-19C, yes. And I made some comments here because I had to analyze it to make it work on my emulator. Now the next check is done. We are we have checked the number, the status speed 3 is 1, so we are already in run mode. The next check is check the status speed 11. There are in total 16 status speeds which can be used in this processor. And we go, next is to check the status speed 5. This is another pin of the ACT, the pin number 3. And this checks if the battery is low. If the battery is low, then the status speed 5 is 0. And if it is high, no, if it is low, then the battery is low. And in this case, there would be called the subroutine. I don't know if you can read it here without my pointer. Here, these subroutine calls, they are responsible for making a blinking decimal point. Just calling them two. The first will switch the decimal point on. The second call will switch it off. In our case, we have skipped it because the battery is not low. The next step is to ask whether a key has been pressed. And this is done again via the status speed 3. It has not only the purpose of reading the program run switch, it has additionally the purpose of reading the PIC chip and asking if there is a key in his keyboard buffer. And this is a special code called PIC keys, question mark. And this instruction, all these instructions are sent to all chips on the board, to the RAM chips, to the ROM chips, to the PIC chip, to the display driver. And all of these chips are reading these instructions. And all of these chips have instruction decoders inside and decide whether this instruction belongs to them. So it's a totally different architecture than today. In today we have only one instruction decoder in the arithmetic logic unit of any processor, and the peripheral chips are passive, like RAM, ROM. They have address lines and data lines, that's all. But these chips, RAM and ROM, have instruction decoders inside. Just for these special instructions, in this case for the PIC chip, there are only 6 instructions, and the PIC chip decodes these instructions. All other chips decode them as no operation. So this is one of the instructions for the PIC chip. And what does it mean? It asks, is there anything in the keyboard buffer? And if yes, the PIC will output a high level on a line which can be read here in the next instruction. The instruction is the status speed 3 set. Now, in our case, there is no keyboard, no key pressed, and we skip. And now, you see, we go back to the go to 151, and this is the beginning of the loop. That's all. This is a complete loop, idle loop of the HP-19C. Check the slider program run switch, check if there's a button pressed, and the battery low. That's it. And now I press a button just for you. I have pressed now the F button, but still not running program. I'm in single step. But now we go again through this loop, and when we arrive this PIC keys instruction here, then we have no jump. We are not going back in the loop, but now the first instruction after having discovered the key press is switch display off. So now the calculation begins and the button will be interpreted, and much complicated things happen here. And then when the key is processed, it goes back to the idle loop. That's all on this.
What do you think of the quality of this code? How do you have an impression of it? Because it's very dense.
Absolutely perfect masterpiece. Absolutely perfect masterpiece. This is compressed to the best you can. But you also have to mention that the structure of the processor and the instruction set is only the instruction set of this time. Today is much more sophisticated instruction set. The instructions, you need less instructions for getting the same results. This is rather complicated. This is a 56-bit processor. Today we have 8-bit, 16-bit, 32-bit, and 64. 56-bit because one number with 11 digits has 56-bit, and the exponent is contained. So the processor has an instruction set which can handle these 56 bits. And it can handle also only the exponent, so a part of this 56 bit. It can handle only the mantissa sign with instruction, add or subtract. The mantissa sign is coded as the number 9 or 0. 9 means minus, 0 means plus. And you can subtract 1 from 0, then you have the result 9. And so you have to think very different to get these instructions working like you want. But overall, they were very sophisticated programmers that time. Even
would you say that it has been written by just a single person? A program like this?
I don't think so, because there are different purposes. One purpose is the pure mathematics, like writing the sign of sine, cosine, logarithms, and these are made first for the HP-35. And who it is known, I don't know the name, it is well known who did that. And they, of course, took the same code to the next generations, perhaps with some modification, some more precision. But the other code for the printer is definitely written by another person.
Especially controllers.
Yes, the printer, this, let's have a look. I have 10 minutes more. I could show you how the printer instructions work in 5 minutes. There is a printer instruction called pick print, and I have to search it. Pick print, difficult. First go in run mode. Now stop, print, and single step a little bit faster than normal. We will end up, after some 10, 20, 30 instructions, we will end up at a print instruction. And there...
The comment that's there is in German, I think?
That's my native language.
Yeah. It was not there originally. The comments weren't there originally.
No, there are no comments. Not even the mnemonics. I just got the bits out of the ROM code.
I see.
So I disassembled, and the codes are taken from the HP-25 from Eric Smith. He already had, I think that he had it from some HP documents, the assembler mnemonics. Perhaps there are too many instructions to get to the print code, but you can imagine there's a lot of search work for finding what is happening here, and I think it is not going well. Oh, I have it. Pick print, there is one instruction. And what I do now, I can enter the operation code 1720 and set a code breakpoint 1720. So now I can run, and indeed I have reached this instruction. When this instruction is reached, the register, C register here, contains the number to be printed. And in our case, it's the number pi, as you can see, 314859264 and exponent 0. And what now happens if a pick print is executed, this instruction, the pick chip will read this C register from the ACT. it has already read this register because it reads it every instruction. So it knows what this C register contains. And when the pick print instruction appears to his instruction decoder, it will write these numbers in his internal printer buffer, not yet start the motor. Because you can add another print command and add even more numbers for a longer line, and you can add some characters also. And but it's very easy to understand. These numbers, the C register contains either numbers or characters. I go through this because I don't want to. Exactly. You see that the printing has been executed. There's the number pi, but also 3 asterisk characters. These were printed by another print command. This is called print number 6, and I miss it here, so I can only explain it. For printing a line with characters and numbers, there have been 2 print instructions follow up. One print instructions with alpha code, and the PIC chip is able to print up to 64 characters. It has a 6-bit code. And when the line is constructed from right to left, so it added first the characters in this case, and then the numbers, and then the motor starts from right to left and prints this printer buffer. I think you have an overall an overview now about this wonderful and sometimes most hated calculator, and I hope you enjoyed this presentation.